Today we'll discuss the modeling of elastic spring elements. The first thing we should point out about these elements is that they have no inertia. They represent just the storage of energy with deformation or displacement within a mechanical system. They represent the restorative forces that the structure delivers in response to any deformation. The restorative force will be zero when there's no deformation inside the mechanical system, and we'll refer to this situation of having no deformation as the free or natural or undeformed length of the elastic element. Since spring elements have no inertia, we don't measure their position. We measure the position of the masses that are attached to the ends of the spring elements. So deformation of a spring element depends upon the motion of the masses that are at either end of the spring element. So we measure the deformation of spring elements in terms of the motion of the masses attached to the ends of the spring elements. If we want to do modeling of spring elements, then we have to decide a few things. First, we have to decide where to put the origin for the motion of each of the masses. When a mass moves, we have to measure its motion with respect to some origin, and this has to be decided. The second thing which we must specify is which direction corresponds to positive motion of each of the masses. So what we're doing is setting up an axis system for each of the masses, deciding where the origin is and deciding which direction is positive. Typically, we'll place the origin for the motion of each mass at the static equilibrium position for that mass. So, if there is no gravity or other constant external forces acting upon the system, this position will correspond to the point where the spring is undeformed. Regarding our second question about which direction to choose as positive, we can choose any direction. Now, for multiple mass problems, it's best to choose the same direction for all the masses. And note that when we choose a direction, we're not assuming which direction the mass is going to move in. For dynamics problems, we never know what direction the mass will move in. It's dynamic. It could move both directions, one direction at one time and one direction at another time. So there's no assumed direction for motion in dynamics problems. When we pick a positive direction for an axis, we're not deciding which way the mass is going to move. All we're deciding is which way we're going to say is the positive direction. Let's look at some examples of setting up our origin in positive direction. In the first example, we have a single mass system with a single spring attached to a wall. We have the arrow symbol with the notation x, indicating the variable's name for the deflection of mass m1, the positive direction, and the location of the origin. If mass m1 moves to the right, the spring will be stretched and x will be positive. If mass m1 moves to the left, the spring will be compressed and x will be negative. When x is 0, the spring is undeformed. That's because we chose to make the origin the location where the spring was undeformed. In our second example, we have a two-mass system with two springs. Spring K1 connects mass M1 to a wall. Spring K2 lies between mass M1 and mass M2. The arrow, labeled x1, indicates the origin and direction of positive motion for mass m1. In a similar fashion, the arrow labeled x2 indicates the origin and positive motion for mass m2. The deformation of spring K2 depends upon the difference between x2 and x1, the motion of the two masses. If x2 minus x1 is positive, then the spring has been lengthened. If x2 minus x1 is negative, the spring is compressed. The origins for specifying the motion of the masses can be placed on either side of the mass. It makes no difference. Because in lump mass systems, the masses are point masses. They have no extent. While we depict them as blocks, they are in fact points. The restorative force exerted by the spring on the mass always acts to oppose the deformation of the spring. That's a key aspect of restorative force. It's basically trying to return the spring back to the undeformed length. Consider this example. We have a mass spring system. The mass is connected to a wall via a spring, and the mass has now moved away from the wall by a distance from its undeformed position, that is x. So the length has increased in this example, and the spring is stretched. So the spring will exert a force trying to oppose this stretching. That is, it will exert a force on the mass to the left, pulling it back. If we make a free body diagram of the mass, and we denote the spring force going toward the left as shown, then we can write that this spring force, F spring, is equal to k times x, the amount of displacement of the mass from the undeformed position. This is a linear spring because the spring force is directly proportional to the amount of deformation. Now note I wrote that F spring is equal to kx. You might have seen this equation before as F spring equals minus kx, and might have a question about why the minus sign is not here. And the reason why is because of our free body diagram. When I drew the free body diagram, I showed the arrow for the force going to the left and labeled it F spring. What that picture means is that this is the positive direction for the variable F spring. That's what the meaning of the arrow is, in fact. It's not the direction the force is acting in. In dynamics problems, the spring force could be acting either way, depending upon where the mass was. But when I draw the free body diagram and show F spring pointing toward the left, what I'm doing is specifying that that is the positive direction for this force. And this variable will be positive when x is positive. And therefore I write F spring is equal to kx, not minus kx. We could draw our free body diagram with F spring pointing to the right. That would indicate that rightward was the positive direction for the variable F spring. And this would be perfectly okay to do. There's nothing wrong with drawing the free body diagram this way or the way we had it on the previous page. But if we drew F spring arrow pointing to the right, then the equation relating x and F spring would be F spring equals minus kx. We need the minus sign because when x was positive, that is the displacement of the mass was toward the right, we know that F spring would be pointing toward the left, which would be a negative value of F spring because the positive direction was toward the right using this free body diagram. So whether it's F spring equals kx or F spring equals minus kx, either one is correct as long as it's in agreement physically with the way we've drawn the arrow on the free body diagram. I now want to turn your attention to the difference between the restorative force and an applied force to our spring mass system. An applied force may cause a spring to deform, and this needs to be distinguished from the restorative force that the spring exerts due to being deformed. In dynamic systems, these are different, In static systems, they are the same, and that's the reason why students will often confuse them. So I have an example here to try to make this difference more clear. And the example is as follows. Let's suppose we have a spring and it's hanging down from the ceiling and we have no mass attached to it. It will be at its undeformed length in this case. Remember again that our springs are massless, and so they'll undergo no deformation due to their own weight. I now add two masses, M1 and M2, to the spring, and because of the gravity exerted on the masses, the spring will be deformed in length, and I'm labeling the deformation X. If I make a free body diagram of this system at equilibrium, we'll have the spring force acting up, which will be Kx, and I'll have the weight acting down, which is the applied force, which is M1 plus M2 times G. And statically, these will balance out. So in this case, the restorative force, F spring, is equal to the applied force. From that balance, we can calculate the amount of deflection of the spring under the load of the weight of masses 1 and 2. So Kx is equal to M1 plus M2 times G. That's the equation of equilibrium, and I solve for x. So the amount of deflection statically under the weight of the two masses is x equals M1 plus M2 times G divided by the spring constant K. And as I mentioned, we have the balance. So there is the restorative force and the applied force, and they are the same in magnitude. But this is not true in dynamics. Let's consider in this example what happens if we suddenly remove mass M2. So here is the situation immediately before and immediately after M2 has been removed. In the first diagram on the left, M2 is present. The spring is deformed by length x. M2 is then suddenly removed. The spring is still deformed by x. It hasn't had time to actually change its length yet. To do so would require it to accelerate M1 and move it upward. This takes, of course, some time, since M1 has some inertia. So the spring is still deformed by length x, which we found on the previous page. And now our free body diagram is as follows. We have Kx as the force acting upward and M1g acting downward, M1g being the weight of mass M1. Of course, K times x acting upward is equal to M1 plus M2 times G. So we do not have equilibrium. But more importantly, you see the restorative force is Kx, and the applied force is M1g. So the applied force is not the same as the restorative force. The restorative force is the force exerted by the spring on mass M1 in response to the deformation of the spring. The applied force, in this case, is the external force acting on M1 from outside the system, which is the weight. The imbalance of forces in this case will cause the mass to accelerate upward, and then of course the spring will shorten and the restorative force will decrease. The key thing I want you to note from this example is that the restorative force and the applied force are different. In static systems, they'll be equal, but in dynamic systems, they are not. And also, the restorative force and the applied force are coming from different sources. The restorative force is from the actual present deformation of the spring. The applied force is whatever is external to the system that is acting upon the system. In this particular case, gravity. One reason I think that this is confusing for students is because of Hooke's law. Hooke's law is presented as F equals kx, and in Hooke's law, F is an applied force, and x is the displacement that's resulting, the stretching of the spring, due to the applied force. When you see F equals kx in this lecture previously, F was the restorative force, and it was responding to x, the amount of deformation there was in the spring. But Hooke's law is ultimately about a static test. And when we do static tests, the applied force and the restorative force are the same. That's the reason why the applied force is equal to kx. It's because this is static. But remember, the applied force does not have to be equal to kx, as we saw in the previous example, where the applied force and the restorative force were different. The restorative force was equal to kx, but the applied force wasn't.